Okay, let's dive right into this. Welcome to The Explainer. I'm Dr. Chem, and today we are stepping into the lab to analyze something that affects literally every single one of us who steps out into the sunlight. Yet it's a topic that is just riddled with myths, regulatory gridlock, and honestly, some truly fascinating chemistry. We're talking about sunscreen. But not just a basic surface-level look. We're going to explore a massive, recent FDA approval that is completely changing the cosmetic chemistry industry in the United States. We're talking about the first breakthrough of its kind in 25 years. Our core mission today is to understand exactly how these sunscreens interact with our bodies, right down to the molecular level, and why this new chemical breakthrough is such a game changer.
But before we get to the breakthrough, let's test what we already know. Do mineral sunscreens actually reflect UV light? Now, if you've ever bought a tube of sunscreen, you've probably seen the marketing, right? Chemical sunscreens absorb, while physical or mineral sunscreens, like zinc oxide, act like a tiny little mirror, just reflecting the sun's rays away from your skin. Well, I want you to reconsider everything you know about the physical mechanics of sun protection.
Because that public belief, it's actually a complete myth. The scientific reality is that both primarily absorb UV light. Recent laboratory measurements analyzing pure zinc oxide, along with commercially available mineral sunscreens, proved exactly this. Now, while mineral sunscreens do scatter and reflect a tiny percentage of light, their primary mechanism, just like chemical organic sunscreens, is absolutely absorbing that ultraviolet radiation.
When we run the molecular animations comparing organic or chemical sunscreens to inorganic or mineral sunscreens, a really fascinating reality emerges. Both types of UV filters act essentially like microscopic energy sponges. When UV radiation from the sun hits your skin, these active ingredients, whether we're talking about avobenzone or zinc oxide, they soak up that harmful UV energy. The molecules get excited to a higher energy state, and then they have to safely wring out that energy, usually by releasing it as harmless heat before they can absorb any more. So they are both doing the exact same heavy lifting.
Section 1. The photostability problem, when sunscreens break down.
Being a molecular energy sponge is exhausting work. Older organic filters, specifically one called avobenzone, are absolutely crucial for UVA protection. Those are the rays that cause deep cellular aging and skin cancer. But they are notoriously unstable. To figure out why avobenzone breaks down in sunlight, scientists in the lab use incredibly advanced analytical instruments, specifically transient electronic absorption spectroscopy, or TEAS. This is a brilliant ultra-fast laser technique. We use it to watch sunscreen molecules in real time. And when I say real time, I mean we are tracking these molecules on a scale of femtoseconds and picoseconds. We're watching exactly how quickly these molecular sponges can wring out their absorbed UV energy and return to a stable ground state so they can absorb more rays. The data we gather from these ultra-fast lasers is startling. Initially, avobenzone offers great protection right around the 350 nanometer mark, which sits right in the UVA spectrum. But after just 1 hour of UV irradiation at normal solar levels, you see a massive visible drop in protection. The avobenzone molecule is literally changing shape, transforming from a highly effective enol form into a much weaker diketo form. Over just 60 minutes, its protective power significantly degrades.
In cosmetic chemistry, this breakdown is called incomplete ground state bleach recovery. Yeah, it's a bit of a mouthful, but the crucial point is this. The avobenzone molecule fails to reset itself completely. Instead of snapping back to its original shape to absorb more sunlight, it forms these long-lived photoproducts. It essentially gets stuck, offering way less protection and potentially even creating reactive states that can cause oxidative stress on your skin cells. It is, quite simply, an unstable sponge.
Section 2. The systemic absorption concern, beyond the skin barrier.
To answer what happens when these unstable molecules breach the skin, the FDA supported a landmark clinical trial published in JAMA. They set up what's known as maximal use conditions. Participants applied 2 milligrams of sunscreen per square centimeter to 75% of their body, and they reapplied it 4 times a day for 4 straight days. And if being covered in that much lotion wasn't enough, researchers conducted 30 separate blood draws over a week. This intense methodology was designed to truly test if these legacy chemical formulations were penetrating the skin barrier and entering the blood plasma.
And 0.5 nanograms per milliliter is exactly what they were looking for. Keep this critical number in your mind. This represents the FDA's incredibly strict systemic safety threshold for blood plasma concentration. If an over-the-counter drug gets into your blood above this level, the FDA demands rigorous safety testing for things like long-term bioaccumulation and hormone disruption. Well, that JAMA study revealed that many of the legacy chemical filters we've used for decades were readily exceeding this 0.5 limit.
Section 3. The 25-year innovation drought and industry stagnant.
Because the United States FDA treats sunscreens as over-the-counter drugs, requiring incredibly rigorous safety testing, unlike Europe and Asia, where they're actually treated as cosmetics, we ended up in a massive gridlock. In 1999, the FDA approved its last new chemical filter. For the next 2 decades, global markets rapidly adopted amazing next-generation filters. But American consumers? We were stuck compromising between mineral sunscreens that left a heavy, chalky white cast, or those legacy chemical sunscreens that were irritating, unstable, and apparently absorbing into our bloodstreams. Then, in 2019, the FDA demanded exhaustive safety data on the older chemicals, effectively freezing the U.S. market in its tracks.
Section 4. The Bemetrizanol Breakthrough, a modern solution.
But finally, that 25-year drought is over. The FDA has officially finalized the approval of bemetrizanol, or BEMT. This is the first new over-the-counter chemical sunscreen ingredient for the American market in over a quarter of a century. So why did this specific molecule break the gridlock? First, it offers true broad-spectrum protection. Second, it has exceptional photostability. It doesn't break down like avobenzone. But the absolute most crucial point is its sheer size. Bemetrizanol was engineered with a very large molecular weight. It is physically just too bulky to penetrate the skin barrier. It sits safely on the surface of your epidermis, intercepting rays and completely circumventing those blood absorption issues that troubled the FDA.
When we look at the UV visible absorption spectra, we see that unlike older filters that only target one type of ray, BMT acts as a dual action shield. It has one major peak of UV absorption at 310 nanometers, efficiently neutralizing the UVB rays that cause sunburns, and it has a second peak right at 340 nanometers, soaking up the UVA rays responsible for cellular aging and cancer. It is literally doing the job of multiple legacy chemicals all by itself.
Furthermore, laboratory research notes that bemetrizanol does not break down easily, helping to stabilize other vulnerable UV filters when blended. It actually acts as an anchor in these modern skincare formulas. Not only does it survive the harsh sunlight itself, but when you mix it into a sunscreen with weaker filters, it actually protects them from degrading. It completely solves that incomplete ground state bleach recovery problem we analyzed earlier.
So, the analytical science is clear, the safety profile is incredibly strong, and the regulatory gates have finally opened. We're entering a new era where we no longer have to choose between a pasty white cast and unstable chemicals absorbing into our blood. I'll leave you with this question to reflect on. With the 25-year drought finally over, how will this new chemistry change your daily routine? Because safe, invisible, and photostable sun protection isn't just a European luxury anymore. It is finally a reality right here. Thanks for joining me in the lab for this explainer, and keep questioning the science behind your daily routine.